Yeah, we got a full house. Yeah, okay, so this is Coffee Compiler Club, and anything to do with compilers and language runtimes, and typing systems, and null and not the null, and parsing and garbage collection, concurrency and bandwidth, and all these things are all good, fair game. It's an open mic, ask what you want. Conversation goes where it goes. I don't have a set agenda. I reserve the right to moderate, never had to do it. You are being recorded live. I will put you up on YouTube generally, not these days, within a couple hours. It's pretty quick. That's my spiel, except I'm going to admit Yorick another time. We'll have 2 copies of Yorick here in a minute. I got 2 copies of Yorick. That's it. It's open mic now, so we go where we want. I did have a request from a guy who's not here, Max Bernstein, to talk about debug info, which if he shows at some point, we'll start it then. Otherwise, sometime when we're looking for a conversation topic, I'll bring up how to do debug info, or what I did for debug info anyhow for JITted code.
We lost our York replica.
Ah, man. Okay, fine. Let's see if we lose this one too.
Get by with the primary.
Yeah, well, let's see if we, yeah, right. I've had them, people fail 2 or 3 times in a row. That happens. What do I say now? So I'll do an AA status update. No theory things going on. There's the York again. We lost the primary. I'm going to readmit what 3rd time. Yeah, because it seems to be stable and functioning. I've been busy integrating into the main. I've redone primitives so that they can behave like a struct when I want to do like the behavior is that all primitives act like capital I integer wrapped primitives, except they take no extra space. So they're value objects that have only their int, but they're strongly typed. But they have things like hash and EQ, as well as operators on them as if they were. There's the 4th time. Here we admit him again. York's just having issues today. Maybe it's time to turn off the waiting room and see if that helps the situation. Yeah, next fail, next try. So yeah, I've been busy integrating the typing theory back into, well, mostly this at the moment, last 2 weeks has been doing the, I got another Yorick. So the one says joining, I got 2 saying joining now, and none have joined. All right, I'm down to 1 joining actively and 1 joined already. Oh, this one has video. Oh my God, Yorick. 4th, 5th time. Like, I think I've hit accept for you like 5 times in a row.
Yeah, it's only the real one that has video.
And you're really quiet. Yeah, no sound
Maybe
at all.
another one can join with the audio.
Yeah. There is chat if it has to go that route.
Is it better?
Yeah, yes.
Yeah, I don't know what it is with Zoom. Like I can host a meeting fine, but if I join, it will like crash. And they used to hack if I turned off audio and video and then turned it on after joining, it will work, but it stopped working. So now I'm in the browser and it finds like 15 microphones, and I think my webcam ratio is like messed up.
Yeah,
like it's
right.
rushed. Computers.
Yes. Well, what are what OS are you running there?
Linux.
Yeah. That's always been
like it's a weird thing. It's probably because I run Zoom in like a container of sorts and yada yada.
Right. Yeah. Well, we still have a pending Yorick attempting to get in to go with the 4 or 5 failed attempts and the 1 active one. So who knows?
Yeah, I'll see if I can get it working in the meantime.
Oh, the extra one bailed out and you're still here. So I claim victory, quit touching buttons.
I'm thinking of another term now. We had like a York bomb.
Yes. There you go. So anyhow, I'm back to doing like operator parsing, and I'm cleaning up how operators get parsed. And I don't know, the typing thing works. I am testing all of the good, glorious typing things with every test that's coming out of the parser. So all my primitive operator parsing tests are also doing the full Hindley-Milner typing thing with much more aggressive testing than I've done in the past. I flipped the work list 4 different times and do a bunch of other things to validate that I'm getting correct same answers no matter how I do it, and it's all going great. So just pounding forward. We do have a new person, Gilbert.
Hey,
Hey, yeah. Can you use the 30 seconds of why you're here?
sure. I'm Gilbert. I'm an undergrad. I'm interested in security, currently working on an emulator that I want to use for fuzzing eventually. And I've just had some issues with the just-in-time compiler I'm writing for it. So thought this would be an interesting place to maybe.
So you're writing
Learn more.
an emulator and you're writing a just-in-time compiler as part of your undergrad. Geez, it sounds like me. What the hell? A long time ago. So what are you emulating?
I chose RISC-V just because it's a pretty straightforward architecture. Yeah.
You got, okay, well, here you are. You got any questions on just-in-time compiling that's having issues?
It's like my main initial issues were mostly on how I wanted to handle register clobbering when like entering and exiting the JIT. For now, I just decided to memory map them to make it simple, even if that is probably not the most optimal way to do it at all performance-wise. But I figured that might be like a good patchwork solution while I'll figure out the rest of the problems and then get back to that in the end.
Yeah, yeah. Like if your goal is high performance all the way down the line, you eventually want the JITted code to JITted code path to be the most optimal, which means you need a classic C style caller register split. And the register allocator has to be smart about always. And when you're jumping from like interpreted to JITted and back to interpreted, you make that path like screw around with registers to make it work.
Mm-hmm.
But if you're like not caring about performance, you just want to get the bugs out. Yeah, do fuck whatever's easiest.
Yeah. Eventually I will care about performance just because it is meant to be a fuzzer, so it will have to like run fairly quickly.
Yeah.
But just for now, I figured since my first time writing something of the sort, I should probably take the easiest path for now, just get something working first of all.
Yeah. Do you have an interpreter already?
I actually decided to just go straight for the JIT, so every code that is emitted is instantly JIT compiled.
Ah, I see. Oh,
So
I find the register allocator is not too bad. You have to have a register allocator already.
Yeah, I haven't.
If you don't have
Looked into
any cross-call convention issues, go pick the C code API so you can just cross-call C code directly and generate C code API out of your register allocator, and it should just be like calling another function.
Mhm.
You're like,
Yeah.
I already fixed this other thing. I'm not going back.
Yeah, I'll probably look into it once I'm like have something working, and then I'll look into register
Yeah, fair enough.
allocation.
Yeah.
Yeah.
Yeah, register allocation's like, sort of like, it becomes a big deal eventually.
Mm-hmm.
In the
sure.
beginning, it's like, I just fucking wanted to work. And there's, by the way, there's good paper out there on testing your register allocator that does an end-to-end test in a sort of stupidly obvious way. That's nice to get the bugs out when your allocator gets complicated. You got a simple allocator, maybe you don't care. You get a complicated allocator, does a better job, you start to care. You want to get toward higher performance, then it's a lifetime project. But along the way, you'll discover that inlining and register allocation are key performance drivers, and they go hand in hand. And you'll badly want a robust register allocator. And to the extent that it's more robust, you can inline more, and that's directly more performance. Oh, I got another York coming in. Who's the other York? I have a York in.
No, it crashed. Sorry, I thought I tried to run it outside of my jail. It still crashes, so I give up.
Gotcha. Okay. I was wondering why I suddenly had another York coming in, and I had a York, and I didn't have a York, and I was like, "What the hell?" Yes, exciting times.
I have a question regarding register allocation. So I had the impression that with 64 bits, so with like AMD 64, it wasn't that big of an issue anymore. So it's still important to have a really fancy register allocator, or
Talking 64 bits or 64 registers?
No, a 64-bit processors, so like 32 registers.
Okay, x86 is 16 minus the stack pointer.
Sorry, yeah, sorry. I was with risk 5. for the moment.
No, it's fine. No.
Um,
The answer is absolutely. So my experience prior to doing the allocator at Hotspot was that once you overrun a register allocator's standard, sort of have more live ranges than the register allocator can deal with conveniently, that once it starts spilling, one good spill deserves another, and you drown in spill code. Then you go look at the generated code, and it becomes something like 1/3 spill code, counting prologue epilogues, which have all these stores and loads, plus all the spills you have every fucking place because the register allocator like blew his brains out and spilled everything. And that turns into like straight up performance. So you dial off the inlining, and then you get less spill code, and the register allocator suddenly comes off of this knee in the curve where it spills everything, and you got more performance, but you're at a lower price performance point because you couldn't inline, because when you did, the register allocator blows out. So the experience I got out of Hotspot. So at this time in my life, I had done like 5 full-blown graph calling register allocators from scratch, plus several other kinds of register allocators. So I, got a lot of experience, and I had been working on other people's register allocators on several different compilers. So I'd seen lots and lots of these things going around. And the answer was you needed, there was another 30% performance gain to be had over a well-functioning, good register allocator and inliner, and everything else in the optimizer has to be working well at that point too. There was another 30%, so it's a big number, by having the allocator never spill more than what you would have gotten from caller, callee, register, prologues, epilogues if you hadn't inlined. So that was a difficult bar to reach, but it was doable.
Does this apply to both 32 and to like x86 and x86 64?
Yes. So I did several different 32-bit registers, PowerPCs and Azul systems and Sparks and Itaniums and whatever. And on x86, they made the stack fetching versions of things a lot more cheap. So an x86 was always clocking higher, and they specifically knew you were going to spill a lot, so they had extra hardware to get the spill code in and off the stack cheaper. And the answer is still the same for them both, that the less spills you did, the faster the code ran, just sort of straight up. And I did a lot of measurements and left and right, and I did a lot of performance profiling, both before Hotspot and during Hotspot. And the answer was always, if I wanted across the board 5% performance gain on everything, everywhere, not a specific, I sped up this hot loop. No, everything 5%. You started getting the register allocator to not spill some stupid shit. Then you could turn up the inliner a little bit, and poof, another 5% showed up. And I did that many, many times at Sun, gradually, accumulating 30-odd% of performance gains there.
All right. So speaking of inliners, you have an inliner for the JVM.
Yeah.
And it inlines some functions. Maybe it inlines a lot.
Yeah.
And then 2 questions. One, can you reflect on the stack from user code?
On stack from user code, the garbage collector totally reflects on stack.
But like random Java that's like, what's my call stack?
No.
Okay.
Now, having said that, I mean, that information is available to the VM. If he wanted to expose it to the end user, he could.
But how do you?
There are some ways to get that information. There is a Stack Walker API ever since 11, I think, that'll let you walk the frames, and you can find out what methods and classes are on the stack, but you don't get locals or anything else like that. Just the
so that's a different.
Itself.
That's what is in your Java architected machine state. What I heard Max asking for is, what did the fucking JIT actually do?
Well, like, how do you? Can you can the user in some way see what the stack should look like if there were no inliner?
That's what Dan just said. Without inlining, without performance, here's the Java architected machine state. Since 11, I've never heard of this API.
So so the inline frames will be available in that API?
Yes, it gives you back the frames that are available on the stack. And and it lies to you about whether they're, it doesn't tell you whether they're inlined or not. It just
Ding.
tells you
Right.
that this maps to the, as Cliff said, the architecture state.
Right.
How does it do that for inline frames?
Well, there has to be an inline map that tells you which frame you're in, and so when it walks the data, it has to read the inline map and
Yeah.
give you back Java objects that correspond to those frames in the inline map.
I made that inline map. So every
Reason-
time the jitter decides he's going to inline, he has, sorry, let's back up a step. When you're parsing bytecodes and you come to a safe point, a place you declare to be a safe point because it's a function call is an obvious one, garbage collection point's an obvious one, a bunch of primitives that throw exceptions, blah, 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 a lot of places. Once per loop, once per recursive call, you declare I have a safe point. You record, for me, it was in the IR, I put a safe point node in the graph and he hooked all the live Java machine state. Even if the JIT had no purpose or reason for that computed value, it was dead from the JIT's point of view. If the interpreter needed it, it was in the stack map, but it was in the IR straight up. And so the optimizer could optimize the shit out of that, but he still had to produce a value there. When you inline, that map just added frames to the map. So it was still a purely internal IR only thing. That was a map from Java virtual machine state, which included the stack frames and the Java registers or whatever, pointing into the IR wad, big wad of IR graph. You optimize, including knowing that you took that safe point info only on a very, very rare path. So the register allocator and the instruction scheduler were totally happy to take the effort it took to compute the actual values and shove it off into some never taken, rarely taken path, right? So you got this, you got what you wanted out of it. The fast path had all the right stuff to do what you needed, but it had enough cookies hung on to such that if you took an exception of some kind or whatever, person hit Control C, debug, blah, 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 you would jump off to this other piece of code that would recompute from whatever it needed to before exactly what the machine state was going to be for the Java architected state. Then it would flip off into the runtime, call into the runtime, having prepackaged this stuff on the stack in a standard stack crawl, the same as a garbage collector would expect a stack crawl. And then the runtime does the stack crawl and does exactly what you're asking for and reflects it into some internal C allocated heap thing, whatever C heap allocated shit, and does now whatever you're going to do with it from there. So if you're going to deopt, you have to repack as a interpreter frames. If you're just doing garbage collection, you ignore everything except the oops. And if you're going to reflect it off to the user, what Dan was saying, then you would take that metadata and turn it to Java objects and hand it back. But that mapping was maintained at the time that you parsed the bytecodes, carried through to the end of the allocator, of the optimizer and the register allocator and everybody else. And they all knew that it was only there for these rare off paths. And so they would optimize the shit out of it.
So we don't do that right now for our VM. We have
You
like
better
3
explain we, you got a
instructions.
bunch of new people here.
I don't have to explain we. That's okay. It's better if I don't. We have a VM for a dynamic language.
Well, you can name a company.
It's okay.
Dude, you gotta
We
be
the
proud of
coffee
who
compiler
what
club.
you're doing.
We as
Alright,
in we,
it's-
the coffee compiler club.
Yeah, he doesn't
Yeah,
even
the
work
Coffee
for,
Compiler
he
Club
doesn't even
maintains
work
a
for
small-
Apple.
No, it's not
Exactly.
Apple.
That's
would-
correct. You don't work for Apple. What the hell are you so ashamed of it for?
That's not the question. I just you remember the incident where I was like, oh no, what if I'm gonna get fired for this? No, I just don't want to bring that into. So I work in a Python VM. I'll say that. And the way we do inline frames right now, which isn't finished yet because I only just got the tests to run after 6 months, is we have like 2 instruction stubs at the beginning and end of each inline function that like maintain a small side stack. I can't remember why we did that instead of the table to the side. I think there's an actual
Right.
feature that some other team relies on not breaking,
Right.
but I'll take a look right now.
In the land of Java hotspot, I very specifically removed all inlining barriers except what the debug info held onto. So you can't look at the generated machine code and point to an instruction that's in or out of a particular inline method or not. Sometimes there's a one-to-one correspondence, sometimes there's not, sometimes the same instructions are there just smeared throughout, but sometimes not. Sometimes there is no correlating instruction, and the next Java machine state point you get to will be valid, and the one you left will be valid, but in between, all bets are off. No mapping possible.
So it's profiling.
Ah, well, that's excellent. Turn the profiler into a bit of IR, let it get migrated around and optimized.
It's not a nope. It's some random third-party thing.
Right. You throw it in the IR and then you hook off to the random third-party thing, handing it the cookies it wants. But don't let third-party IR. So a huge.
It's basically it's like BPF. It's some other thing that just like runs on our process.
Is it a sampling?
Yeah.
Right. That's why, Cliff. Yeah. You know, Cliff wants you to put it in the IR so you can SSA everything.
That'd be cool.
That's his middle name. Cliff's middle name is SSA everything.
Two different issues here. One is you need random stack sampling to get any valid answers out, not safe point sampling. And the other one is the people who like to jam shit into every method to profile hurt the profiling so badly that they get shit for profiles. That the Java went down this path, and I told the JVM DI, TI, PI team this was stupid, don't do it, and they did anyhow. And lo and behold, it was stupid, and it got hurt so bad, and they got a big black eye, and they had to back way off. They tried to inject, hey, I'm going to put counters in on every method entry and exit in a way that can't be broken out by the VM. Soon as the VM or the jitter gets a hold of counters that are known to be not aliased and known to have a bunch of other useful properties, he can do the classic fucking Loris ball count minimization game behind your back for you and give you those identical counts at a tiny fraction of the cost that you're going to get otherwise. So I don't know. I had people would, they would throw in hard, unavoidable counters at the start and end of every method that turned into, like 50% slowdowns, like big number slowdowns,
right,
which completely brutalized your actual profile. Plus, the giant code bloat prevented
it sounds like reference counting. It's so expensive.
Okay, yeah, all kinds of follow-on effects that were just ugly. So anyhow,
we also have reference counting.
Ah, I might have been teasing you.
Well, reference counting is just as bad, but it's fine. And people who do reference counting in JITted code, like typically optimize the fuck out of them on purpose. They know what they are and they optimize them. Same for performance counters.
Yeah. We don't inject any code to do the call. It's like it just walks the RBP chain and like pulls out some information.
To do the profiling?
Yeah.
Yeah, but the key there is random stack sampling.
I think Kirk can explain, though, there are some benefits to the sampling profiling that you can't easily achieve with what you were describing. But I think for optimization, Cliff, your approach is probably easier and better.
Well, it doesn't screw up your code gen, so therefore sort of dramatically change the very thing you're attempting to profile.
Yeah, I agree with Cliff. I mean, random stack sampling is the way to go. With that, I find you can go at an incredibly low sampling rate, so you don't even mess up hardly anything. If there's anything statistically significant happening in your runtime, random sampling is the way to find it. And people are looking for who say like, well, it only lasts like, I don't know, like 100 nanoseconds. Well, if it's statistically significant, it will show up. And if it isn't
that what Max was arguing for, though? Or did I get it backwards?
I'm not arguing for anything. I'm saying that's what happens, and that's what we need the little 2 instruction stubs for, is so that they have a stack to walk. Because people, if we were like, actually the inline frames won't show up in that, people will get really annoyed.
Yeah, the whole thing, the whole bias towards execution for CPU profiling in my books is just, I think the whole industry suffers from what I call CPU envy, and because of that, it's just they're completely missing what's going on and on in the processor and what's really happening when they just focus on these things. It's too myopic a view to really truly understand what's going on.
But I think what Cliff was describing was the idea that as you detect any patterns, you can rewrite it to detect more patterns, right? Isn't that kind of the gist of it? So you can focus on the hotspots specifically.
Why do I care about patterns then?
Yeah, I
don't want to make that assumption because that's going to bias my sampling.
Yeah,
I don't want any bias in my sampling. Well, except for a random bias.
Right. All right.
Isn't the sampling inherently biased though, right, towards safe points?
It's always. Your sampling is always biased. No matter which sampling technique you use, it's always going to be biased.
Fair. That's
just
fair.
Understanding the bias and understanding which bias is going to work in your favor and which one isn't. So if you're biased towards random sampling, in my experience, that's going to work best.
So safe point profiling gives you a very particular view of the world that is useful in some contexts and highly, highly skewed in others. So the problem is if you don't recognize that you're getting the skewed answer, you can totally get fucking lied to by the profiler and completely misdirected.
Well, here's where you're blind, right? In the JVM, you're completely blind to uncounted loops.
Yes.
Uncounted loops have no safe point in them. You'll never, ever get an uncounted loop showing up in a profile.
Yep.
But uncounted loops can be responsible for like 20, 30, 40-second GC pause times.
Huge. Yeah, right. So the uncounted loop optimization hack was the answer to tight, hot inner loops for which the safe point itself, once per loop iteration, was a significant fraction. So I made an effort to clean it out as best I could, but big slowdowns would happen if you had a safe point in those hot loops. Later at Azul, I did unroll and jam, and you would now get safe points much more frequently, but you would still get them way less often per amount of execution than you would expect from a random stack sample. So random stack sampling still tells you where the CPU time goes. Now Kirk's got a different point, which is a lot of time it ain't your CPU is the issue, but random stack sampling will tell you where the CPU time goes. Safe point sampling tells you where you have common safe points, but they don't have to be aligned. You can have common safe points in one place and hot counted loops, in another place, and no safe points. So for the longest time, the Oracle JDK, JIT, whatever, hotspot, the official one, didn't do anything with the hot counted loops, no safe points in them. So you got 0 safe points, and so 0 ticks in your profiler, and sometimes giant GC pauses because there was no safe point to pause at until the loop finished. So that's one thing I wanted to mention once for Max. When you do the random stack sample and you have these prefix postfix bits, so somebody gets a frame, they can tell it's inlined or not, that there's 2 lies going on here. One is that, when I'm done with inlining, there ain't no fucking border for the inliner to say I'm in or out of the inline version. There isn't such a thing, right?
We don't do code motion yet.
Any amount of common sub-expression elimination. You inline a bunch of getters. As soon as you do CSC, you got one getter for them all. You're not in or out of any getter.
We don't have that either.
but you're going to head there. Like CSC is like a major performance optimization. I totally can see this happening, and you begin to lose the border. Okay, so the next thing is that when I did the random stack sampling crawl, I will give you the best effort inlining point. So I'll fake it, and it won't be perfect, but I'll tell you, you took an instruction here, it's in between these 2 safe points, and I'll record the nearest safe point as part of the stack crawl, so that later when you interpret, not during the crawl itself, which is just literally record a PC, grab the BP, go backwards and repeat until I got my stack and get the fuck out, right? So it was 100 nanos, like Kirk was saying, to get those profiles. But when you interpret it, you had the safe point info that was nearby. From the nearby safe point info, you could derive a best effort kind of sort of look like this, including if there were obvious layers of inlining, you would get that.
What do you mean nearby? Like this thing right now, it just goes and walks through. It's kind of like a kernel reading user memory. Like
Yeah.
it goes, it's like, you're okay. It reads
Yeah.
this byte. And it's like, oh, you're this kind of frame, and it
So
just kind of walks the stack.
I would take the interrupt at a random PC. I would take the program counter and reverse it to a hash table to give me the JITted method, right?
I'm asking
From the
how it's
JITted
going to find
method,
that hash table.
I'm sorry?
I'm asking how it's going to find that table.
From inside the interrupt handler, the table's put in was baked into the interrupt handler. I gave, at the time I start the Safepoint profiler, that I'm getting X beats a second from the profiling, who's going to probe my stack. The machine code that probes the stack and crawls it as he goes has access to a hash table that I've set up ahead of time off to the side and given him the address of a hash table. Here, Mr. Stack Probe Crawler, is your hash table for how you interpret stack frames.
Oh yeah, we don't have anything like that. It just kind of.
I understand. I'm saying it's not hard to do. It's just some setup you have to go screw around to do. Once you got to stack that hash table, the probe gives you a metadata, a hook of where your function is, and it gives you shit like the reverse for how you go up the stack. I didn't do what you just said, which is I had it like I reserved on x86. There is a calling convention that reserves a second register BP that you always guarantee is set up. Last instruction in, first instruction out. You set up and tear down. That lets you unwind a stack without having this register map. I put a register map off the side. BP was a standard everyday register. It got used, so I had 15 instead of 14 registers for my register allocator. And then 15 versus 14 actually shows at almost that exact ratio. It's a 8% gain in performance, just like straight up. So I do the reverse the hash map. I got the size of the stack frame. I unwound again. There was one little diddle I had to do. If you were catching the stack just at the stack frame adjustment instruction, I checked for that special case. Other than that, I unwound to the next frame up, which immediately only ever landed you at a safe point. So you got, for the frames up, you got safe points directly, but you only needed a hash table on the first dude. The safe point guy could have the info as well, but I actually hash mapped all the way up. It was all fine. But you needed it hard on the first guy. And then the interpretation guy comes along later offline, not while the code's running. And he looks at the probe he got, and he does the same hash table, gets the whole function again. And then he says, well, there's a bunch of safe points, and I'm here. Without interpreting the basic block layout and the like, I'm going to assume that the nearest safe point on either side is the one that I'm going to pretend like that was the one I was at, right? And it's not true. It's a lie, but it's a close lie. Closer lie than what you get for safe point profiling.
Does the JNI have any exposed functions that can that need to be able to pull out the full frame, like the full backtrace, basically?
Everybody who does an exception throw only does it at a safe point, and they pull out the whole thing. The
As I remember, there is a patch to the JVM to preserve the frame pointer, so the stacks aren't broken.
Not sure where that one.
By
There is
default,
there's a
JVM.
patch.
Oh yeah. They turn it into a flag that by default the JVM uses all the register available, and that includes the RBP register, if I remember correctly. Yeah.
15 versus 14. Take it.
Yeah. So you can.
But
so
the
prepare the stack.
The JVM itself crawls that stack to do garbage collection, to do exception throwing, to do there's a half a dozen other things. Like at Azul, I had a list conveniently written out, actually close to a dozen different reasons to crawl your stack and interpret the JVM architected machine state. It was pretty heavy duty in terms of, there were a number of use cases. What Dan had said with there's an API at 11, I don't know this one, that says you can go get that as a reflective metadata, would be the same thing. You just crawl the metadata.
So in our case, if we have the JIT emits code, there's like someone called some native function. So we just emit a call to that, and then somewhere like way deep in that native stack, it can be like, all right, what is my current interpreted stack?
Yeah.
And so we can't unwind that to the machine code, do a lookup in the side table. Like it's just on it's this the push and pop, like 2 instruction bit at the end of each inline function happens, like modifies the thread state, basically. So this thing can happen.
I see. I certainly never modified thread state in inline, because that was the whole point of the inlining, was to make that cost overhead disappear. Separately, when I call out to native code, I put a hook on the stack that I can crawl through easily. So if I'm starting, the stack probe starts and says, I don't know where the fuck you are, because you're not in my hash table of known JITted code. I'm going to assume that I'll find a cookie, that I put a cookie down that is the last point the stack was known valid in Java, running Java code. And that was a global static location that we just slapped down. You made a native call, you stuck your stack pointer into this global, you throw your program counter into the global. The act of throwing the program counter in the global unlocked your stack. So while you're running on your own stack, or your own CPU is running your own stack, you own your stack, you can mutate it freely. Garbage collection cannot mutate your stack, right? Because it's a blur. It's like super fast changing constantly as you go up and down. As soon as you call off to native code might block for IO for the next month. Garbage collection has to happen. Your stack has to be crawlable. So you have to unlock your stack. So when you call off to native code, you unlock your stack. Well, how's that done? Well, you store down a non-zero over your program counter and your stack pointer, and the act of the last of those 2 stores is on the clock cycle unlocking your stack. Now garbage collecting can freely mutate your stack. It can be crawled in all possible ways safely by everyone who wants an actual architected Java virtual machine state, not the profiler who doesn't fucking care, but everyone else who cares can crawl it correctly. When you come out of the native, you have to relock your stack, because maybe the incremental concurrent garbage collector behind your back is busy mutating your stack frame, and you'll get pre or post garbage collected bits. You can't do that. You have to get the correct ones. So when you come out of the native, you have to relock your stack. How is that done? You cas in a 0 over the program counter and the stack pointer, and the act of that cas claims your stack. And if you can't cas it, that means the garbage collector's got it, and you need to go block until the GC goes your stack. So there is I give a long talk on just how Java does in and out of native calls and why it's so fucking complicated. Half of it is because I want the JVM, the JITted API to be the most efficient possible. Java has stronger typing. There's no var args, so I don't need to do the stupid C var args API call. I can pass floats and float registers and ints and int registers, whatever. I have to handleize everything so that the JVM can have a collector that doesn't do pinning, and while handling off pointers, Java pointers to runtime. We talked about this last week. You missed. There's a cost to doing this, but it's way more better in the long run to separate the VM from native code, and the native code wants to diddle with the VM's objects by querying them or storing them or doing things with them, allocating them, whatever, but you never give them the direct pointer, because that pins your garbage collector down to being a pinning collector, which defeats many interesting garbage collection strategies. So you always give him handles. So he's only stuck with handles. The native guy only does handles. And if he cheats and lies on using a handle, he breaks, and it's his bad, not your bad. So you have to handleize going into the native. You have to handleize coming out of the native. Because it's Java, you have to do locking or not according to synchronized natives. Bullshit, fine. You have to lock your stack and unlock your stack for garbage collection. There's like 3 other things I do during that transition phase, profiling things and the like.
In our previous VM, we did have, objects and handles, and this one it's just reference counting, and
Yeah, and you don't do a moving collector.
No, you just give them you just give them the object, the reference, and have fun.
Yeah. All right, you can declare I gave up on that one. Moving collectors have a performance gain because you get to compress your heap. But they require some complexity.
We're working with what we have. We're building on top of an existing runtime.
Yeah, I get it. I get it. So I would claim that you still want to ponder locking and unlocking your stack going in and out of the native, so that you can have a concurrent collector if you're going to have such a thing. Like you got a cycle breaker going around. Don't you have a cycle breaker?
It's
don't defend. It's all fine.
We do, and not functionally nothing's concurrent. Like it
Okay,
kind of is,
fine.
but not really.
Yeah, then you don't care. If nothing's
Yeah.
concurrent, you don't care. You might still not
It's
have a
Python.
cast, but you put a cookie down as you walk into the native saying, and here's where you restart the Python stack. Right?
So if I think this was the decision to do the 2 instruction in and out push pop was so I wouldn't have to go muck with the sampling profiler, but that might have just been the wrong move. I think given your tip about the cookie on the thread state to at native calls,
yeah,
that might be the only reason the profiler might be the only reason to keep.
Okay, so the next cute hack that we do at Zool Collector does is all threads are on 2 megabyte aligned stack boundaries. So your thread local storage is a low 4K. And so I take your SP and I mask off the low bits with a single mask instruction. That's the base of my stack, my thread local storage. And that's where these bits go. And I throw my 0 down or my stack pointer down right then and there. So there's an API that says in 1 instruction, 1 clock, I can get to my thread local storage base. Makes the overhead getting it out of your native call lower. Same for all kinds of locking hacks and the safe point profiling, the safe point bits. Do I need to stop at a safe point? Somebody wants me to stop at a safe point. How do I test that I'm at a safe point or not? Well, sometimes it's obvious, but sometimes I have to actually have an instruction to test it. And the test for it is grab SP, chop the bits off, test a low order word in base of the stack frame.
Isn't that managed by say like a page fault in the JVM?
We went back and forth on that. It doesn't actually matter a whole lot. I think that we left it at a 4-key boundary. So in x86, the OS can decide that that page is not being referenced and toss it out. And it'll page fault if you touch it, but it's not, that's the actual read barriers do page faults in a meaningful way. The thread local storage guide does not, but a safe point check is load a word from memory. It's actually short bits, load some bits from memory and jump not equals 0. Okay, if you set bits in there, those are the things you have to do at a safe point. If it's 0, you got nothing to do. It's entirely predictable because you rarely any one safe point ever hits. So it gets cached in your L1 cache, whether the OS throws out the backing storage or not, I don't care. It's an L1 cache hit with a highly predictable branch. The cost of actually doing a safe point check is basically half a clock cycle. All thing on a modern x86, it's really cheap. But the actual thread local storage itself is not. Now, there are page guards for overrunning your stack. Those are running with meaningful TLB faults. So like at the end of that 2 meg page boundary, there are some 4K guard pages. And if you flip one, you're required when you JIT code to guarantee that you probe at least every 4K into the stack if you're going to consume more than 4K on a single frame at a time. So if you make a stack frame that has more than 4K on it, fucking giant ass stack frame, but maybe you allocated an array on the stack, you have to probe 4K for every 4K you're consuming up. Okay, as soon as you probe and it throws a fault, the guy decides, oh, we're going into stack overflow mode. And he then unguards another page to let you make forward progress. And he sets the safe point bit. And at your next safe point, you'll throw a stack overflow. So you have to be able to run forward when you're near the edge of the stack. So you have to unguard a page. You have to have a cheap way to tell that you're running out of stack. So that's the probe into the TLB managed faulting page. Is that
Interesting. I've never seen that. That's cute. I like that.
okay? Well, there you go. Perfect safe point stack, perfect stack overflows. All stack overflows occur at some exact Java bytecode safe point. There's not a random I barfed and I died. You get a correct answer, but the actual point where it gets thrown is just some arbitrary safe point. And there's all these JCK tests that test this shit, by the way. They update globals in various places and they race up the stack recursively, endlessly. As soon as they JIT, the JIT decides he can inline and shrink the frames, and the stack frame for the interpreter is pretty big, but the stack frame, the JIT's really tiny, and you get like 10,000 iterations before you run out of stack frame, and he's He validates that you got a stack frame thrown at some reasonable place. He fucking catches the stack overflow exception, does other things while catching and throwing stack overflows, and confirms that, you know, you get a perfect virtual machine answer. There are no holes in that corner case. This sucked to get it right. and get it performant. You know, the non-performant answers, you just fucking ask the question on every function entry. Hey, I'm about to run out of stack. Okay. Throw an overflow instead.
No. Better to let it happen.
Fast answer. I just had a guard page and you unlocked it and threw the bit, and that your next and that let you run, and the next safe point you blew out, died. I guess the other piece of that is I would throw, when you unwind at a stack overflow, the requirement the unwinder had was he could always throw stack overflow whenever he wanted, even if he had frames available on the stack. But he would guaranteed then unwind however many frames it took so he could reguard the guard page at a safe point. And so sometimes you got unexpectedly more throws, even at your catches. The catches would get ignored because I would claim stack overflow immediately inside of your catch. That's a valid JVM interpretation. And throw again, think, go again and again and again until I unwound enough. Like you threw the guard page, and then you ran in and nested a bunch of layers. All those frames had to be unwound, even as they caught or attempted to catch.
So I'm still thinking about that point you made earlier on the going from 14 to 15 registers gave you about an 8% boost.
Yeah, it's
I'm
stupid.
curious if anyone's making use of the 512-bit registers now for general purpose use, right?
Oh,
Like
I bet
with
you the JVM.
because I've never gotten to play with those. I don't know, Matt.
So when we got the better SSE registers over the damn 8087 thing, they were fat, but we just used them like 1 word per register. We didn't do any packing and unpacking games. SSE for hot arrays with packing and unpacking came much later. For instance, you got 8 new floating point registers that were actually like real floating point registers. You used them like floating point registers, and that was a big game. And that was easy to add. So if you added a second set of registers that had a register numbering that was reasonable, your allocator could do it. You go into the machine description file, you set it up. If you had giant wide bits and you wanted to pack and unpack, you know, kind of hands off, okay, that requires SSE short form vectorization games. We're not doing that.
Right.
But you get just, here's some extra registers. Allocator could go to town on it, not a problem.
Yeah, it's just
J9 on the S390 platform. We did play some of those games on the 32-bit VM on 64-bit hardware. We would stuff two objects into the 64-bit registers.
Yep.
The problem is you end up having to be so careful about anything that does sign extension that you don't end up trashing the high words, and the costs of playing those games became so high that we ended up ripping the code back out.
Backing out. Interesting. Certainly when the land of 8 x80, the pre x86s that I did for hotspot, I had 8 registers, 1 for the stack pointer. You know, BB desperately wanted, because you went from 6 to 7 registers. We did pairs for longs, which gives you 3 pairs out of your 6 registers. But the pairing is a different thing because you didn't have sign extension. So that was a different issue. Yeah, that's interesting.
Isn't it a rather large restriction that SSE registers are not the general purpose registers? I'd assume that if you use the SSE registers for random stuff, you'd have to shuffle in and out of them quite a bit.
Right. No. I'm saying we used them as they were general purpose floating point. I didn't say floating point. You say that. General purpose floating point registers. So 1 float value of either 32 or 64, no packing, unpacking. Yeah. What I just heard, I don't know who it was. It Dan? Who said that?
Yeah, it was Dan.
Yeah. Okay. What I heard him say was, if we did 32-bit values in 64-bit registers and we try to put them in pairs in the 64 bits, the sign extension caused so much grief that it wasn't worth it. Now here's an interesting one. So in the land of doing long math, so I started doing, Sun came out with a 64-bit Spark for x86 had a 64-bit VM, so all 32 bits, blah, blah, blah. I had a well-working 32-bit operation where I would take longs and split them into two 32-bit values with an add with carry in the IR. So the IR had a high word and a low word and add with carry, but the high and the low word were just adds and subtracts and multiplies and didn't care. But you needed an add with carry. And I did long math. And it turns out that at that time, the great consumer of long math was crypto calling big integer. So big integers do shit like grab the high word by shifting right or shifting left, grab the low word, mask off, sign extend, yada, yada. They do half of 32 in the 64 all the time. Well, this mapped perfectly to an IR, which split them into 32-bit chunks because one half of the other was always aligned perfectly as a single register. And you got effectively 7 registers to hold halves of however many longs, and most of the longs only wanted one half anyhow. When we flipped to going to register pairs, we took a big hit on web services running crypto, running big integer math on an x86 because you only had 3 long pairs. So for the longest time, we had 2 modes to run longs in. Longs were a single register for Spark 64. Longs had to be a pair for Spark 32, but they badly wanted to be a pair on x86 32. And it wasn't until we had 16 registers of 64 bits that x86 was better off using longs as an entire register. But it's still not what Dan was talking about, where 2 unrelated values were kept high and low. If I had 2 values in a long, they were the same value, but
Yeah,
it
so
typically only wanted half of them.
A 512-bit registry would be some serious packing and unpacking on almost every operation. But you could think of it as instead of thinking of it as just a general purpose register, you could think of it as a cache or just a fast line of 64-byte line, right?
Yeah, I'm trying to think of how you would treat it, how you would know to use it as a cache. Like here, I'm going to spill to a 64 to whatever AVX register instead of spilling to the stack.
Yeah,
that might be doable in the current allocator. Like the allocator has brains to know that he treats the hotspot allocator treats stack slots like another register, but they are moved in and out of with load and store ops. But there's an infinite number of them, and he register allocates them like he register allocates anything else, except it's an infinite number. He never has to spill them again. That turns into really tight stack frames, which is another performance goodness. And generally good register allocation, but occasionally get a reg to reg move, which is really store, load, in and out of stack frame. But you could go store and load in and out of something else like a spill too.
Is using that as a cache actually going to give you a win on like an x86 that is already cheating and being like, hey, this got written out and read back in quickly?
Yeah, I don't know. I
feel like the x86 is already rewriting your code in ways that might be more effective if you don't trick it.
Yes, exactly. And here I'm not certain. I know that in various versions past, the path to in and out of the stack, storing things from small offsets off SP into a store buffer hardware was shortcut because people did that all the time. So not just push and pop, but you just did move register into SP plus small offset, and a short time later you said move from SP all small offset back into register, and he knew that you were just doing a backing store. If you didn't move the stack pointer base and there was no other A-listing going around, he could shortcut that. And I don't know what he did and how he did it, but I know that was always faster than it looked. It was still better to never spill at all. So that was the 14 versus 15 registers gave you a win. But if you spill to the stack, you got one number. And if you spill to fixed known locations in low memory that was based from a register, you got a different number and the performance of that.
Yeah, maybe CPU architects just added another hidden register to the register file for exactly these purposes or something.
Yeah. For instance, you could say, I'll throw a hardware flag bit if anything overlaps with my stack pointer in any other register. As long as no one overlaps, then it's completely unaliased. And now SP plus small offset is identical to having a renamed register. So I'll just throw it in the register renaming buffer directly, and it never hits the store buffer at all. Later in life, if it never makes it out the back end of the pipe, I'll have to actually write it to the store buffer and make it right. But I assume that you're going to pop the stack and throw those all away, and they cheat and they become register rename buffers. And that might have been what they ended up doing. I don't know anything, I don't know how it goes, but I know that with performance is different, the better. Data bypass delays. Yes, there you go. I have no idea. And then the downside is you had to have funny instructions to pack and unpack in the middle, or I assume you would, and I don't know how that would go. I assume you could do some sort of extract from one 512 bit register into
That's
another.
the thing with the AVX 512, you can treat it actually as quite a few different fundamental data types. I've never actually written code using it. I just read all the docs, but I think it handles 8-bit, 16-bit, 32-bit, 64-bit, and it may even have a 128-bit mode now. So.
Any of these, we're missing some of these docs in the chat. Some of these links in the chat are not in the docs, if some people want to cross them over.
Now, what I'm thinking about, what could be a potential performance pitfall with using these large registers as cache, is that one has to be very, very careful that if you use those large registers, and for instance, like the AVX 512, you also need to encode all the instructions around them as VEX encoded instructions and not as SSE encoded instructions, because SSE encoded instructions, like with the rex prefix, they retain the upper half or whatever part you're not using for operations, and VEX encoded instructions zero the upper half of the bits you're not using, and the mixing instructions, both SSE and AVX encoded ones, is rather slow on Intel, because they kind of have to change the state of this machine underneath that does the operations. I'll check whether I'll find the article. I found it quite interesting.
Okay. I would think there'd also be an issue of callie saves. So maybe if I actually spilled into an AVX register and then I crossed a function call I couldn't inline, I had to go save or callie save or caller save the AVX register, and that just lost all my gains. I don't know. You're probably better off with a smarter, richer allocator than trying to stuff in and out of AVX. For general purpose calculations.
All right, I think I found it. I posted it in the chat. If you scroll down to the, I think to the half of the page, there's this nice state diagram from Intel that marks things in red, which should be avoided because they are really, really slow. And
I see.
And in practice, either you're using the zero upper instruction excessively, or you just avoid using SSE encode around AVX instructions. And yeah,
Okay, fine. I'm not currently in that game, so I'm not gonna play it.
Yeah, but it should be fine as long as you don't mix and match, right?
That's what I heard. Yeah.
yeah, that's one approach.
Yeah. The answer is easy and won't use AVX. But I'm
That
not there,
sounds
so
like
I'm
an
not
almost
doing it.
titanium philosophy.
Oh yeah.
Mm.
Well, it's because when they introduce some of the features, they actually reuse some of the same units. So they have to have an internal dirty flag, and then they mess you up because then the next generation, sometimes they'll duplicate the units or duplicate the registers, and then it doesn't have the problem. So it's like you have to know every single detail. It's crazy.
This is not the first time I've seen that transition where you flip from having a state that was expensive if you mixed and matched to having the state where it was cheap to mix and
And it's
match to
even-
having it where you didn't care for the other old one at all. It was a very slow transition with constant fiddling.
It's
and
even
tuning.
worse now because the newest CPUs do not have a uniform instruction set across the cores. So depending on which core you're on, you have different. You can have different code running. Specifically, the E cores are Atom based, and the P cores are Ice Lake based or core based. Matt, you can help me out with all the code names here, and so what ends up happening is you can run AVX 512 on the P cores, but if the thread gets scheduled on the E cores, holy molasses, something, all the wheels come off at the same time.
Well, that should be like tagged for the OS scheduler then. Somebody should have a clue.
So product marketing, a product manager at Intel actually just decided that they would disable AVX altogether. And so, but it's firmware controlled, so you can still get the AVX. You just can't schedule onto the efficiency cores if you're using it.
So are they
webs we weave?
Are they not doing some kind of transition from the efficiency cores to the performance cores if they hit the instruction?
It's all handled by the OS.
Fuck. Matt, you're talking about this key on my keyboard that I never touch?
So the OS handles the scheduling, and if that instruction shows up on the E core, it's just not going to decode it. It's going to be a fault.
Yeah, right.
So when it hits the decoder, it'll fault. Yeah.
So how's the fault managed? Is that turned into a full, I need to context switch this thing over to another appropriate core?
I assume I assume it goes to the OS. I mean, that's a hardware interrupt handler, right? Like, or not
There is an option in BIOS that allows you to use scroll lock to disable scheduling on the E-cores. So if you are old enough to remember the turbo button.
Yeah.
God. Oh God.
What if I
Did
need
you all see
that
the
scroll lock
paper?
key for Excel?
Sorry, what was that, Aaron?
I said, but what if I need the scroll lock key so that I can move Excel around without the cursor moving?
No AVX 512 accelerated Excel for you.
The turbo buttons. It's been a long time since I had a turbo button.
Yeah,
I had a stupid bad old war story about turbo buttons. I probably should share. I was first job out of college. I'm like hacking away on some Z80 core thing for doing data entry, whatever. Fine. Had a Z80 math package. It was really sucked. Z80 had a second set of registers that no one was using. You had to flip the entire register set. So I did my math and flipped back. This sped up the math package and the core thing. It gave us like across the board, almost 2x speed up for the package. And I showed it to my manager. I was like, oh my God, this is so awesome. And he was like, oh my God, it's too good. We can't show the end customers. If things speed up by 50%, they'll just nod silently and say, thank you. If things slow down by 10%, they'll scream bloody murder. So he literally made me put a delay loop in so that every generation that we return for the next 2 years afterwards, we just dial off the delay loop and keep the performance the same. It's just like it was the turbo button, just like, turn off that little delay loop a little bit. Okay, we're all good. Sucked. Part of that conversation turned into shit like, what color was managers, what color was my monitors mattered, and I didn't care for this or that. Or we had some guy that literally they said, we'll put you in a pair of pedals that you can pump and tie it to the video monitor brightness. And if you pump the pedals, it'll go faster. Of course, it just made him busy. So, everyone was happy. There were a lot of funny war stories. That one wasn't my war story. That one I got fed from the same guy that would say, put the delay loop in. Shit.
So was that database MOAV?
Recognition Equipment Incorporated from umpteen years ago. I still used to have a piece of, I had a leather icon floating around. They did some amazing shit in hardware. There was the optical, those are the guys doing analog optical character recognition back in the early 80s. They could read all the checks that Citibank in New York City would read in an evening. So 100,000 odd checks. They did post office address reading. They did a bunch of stuff like that. They would read this much text from a check or an envelope when it was moving through a sliding, rubber belt at 60 miles an hour, literally 60 miles an hour. And you would feed a hopper like this and would just drop the hopper like that. Shit would fly through and they would read it with an optical analog character reader with a 97, 98% correct rate. And the leftovers had to go by the data entry, which is I was working on, and have an operator stare at it and say, oh, this is what it actually was supposed to be. But they could read optically characters. So that was done. This is the crazy thing.
The post office was using those optical analog mail sorters until 2019.
Really? I can believe it. They were fucking good.
I mean, they're digital now, but
yeah, right. So a font back then, I don't know what it was when it turned. A font was an array. A CCD camera put out an array of 64 pixels, and a character was an array of 64 resistors that would, scale each individual pixel up or down, and then sum them all in total. If you crossed the threshold, you got a hit for that character, which meant that the resistors all had different depths according to what they wanted the character to look like. And fine-tuning the character read involved an engineer taking his pocket knife out and shaving a little bit off a resistor because that would increase the resistance. And I watched them do this too. It's just like, holy shit. This is analog by like serious analog. Yeah, fine. Okay, so dumb war story done.
Well, what's really cool about that technology is you can use the same thing to do digital audio conversion. It's called a resistor ladder, and basically, as long as the resistors are very close to perfect, you can peel off each binary, each power of 2 level with another ladder, with another layer on the ladder. So,
okay, yeah, that makes sense to me.
So, believe it or not, that's actually being used still for some audio equipment.
Wow.
So, for example, volume controls that have like 1,000 resistors in them for, instead of a pot or or digital.
Yeah,
or
right.
I mean, analog's fast.
Yeah. It's all good.
What I really want to know is, what the Amazon bill is for the guy running the universe simulation. It's like, because every time Intel comes out with a new chip or NVIDIA comes out with a new video card, I mean, the bill has to go up, right? Like, I mean, it's simulating a lot of cores.
Yeah. Unfortunately, I don't have that job, so I don't get that. I don't get to write that. I don't get to get that bill. All right.
So if you don't mind me going to a totally different topic.
No, I'll say it's time for a new topic.
I was wondering if people had opinions on core dumps versus a stack trace that also tries to go crawl the heap and get more context. And like, if you want out of your VM a core dump like thing, should you just core dump your VM, or should you do I'm going to walk everything that's not dead garbage and serialize it out in some way?
I have my war story, but The old hotspot when I left Sun crashed, dumped just a few things for every thread. So not the entire core, it's too big. But something for every thread, and made an attempt to crawl stacks and shit. While I was at Azul, first time I took an update from Sun, some bright soul had increased the crawling smartness, except they had done it in a dumb way, so that when they would crawl and they would fail the crawl and they throw another exception while crawling, they would catch the exception, turn off that attempt to crawl, and crawl again. So the first time I got a dump from Sun, I tried to integrate into Azul VM. I found no fewer than 20 broken crawl attempts nested deep before I could get to the actual fail that I was trying to get. That was the crawler itself was throwing exceptions. The crawler was crashing and then crawling the crash of the crawler, crashing the crash of the crawler.
Yeah, in a traditional core dump, you're probably not going to need to core dump while you're core dumping.
Well, that was the problem. Yes. You're right. The smart crawlers need to be like filter the shit, because they're going to be handed total random garbage that's more adversarially almost correct than you would expect from random numbers.
I'm just trying to ask the question, why?
Why did they try this?
No, not you.
No.
Not a question for you.
Oh, the question of why is it useful to get a core dump?
Sorry?
So often there's a running process that's behaving kind of wonky.
Yeah.
And you don't necessarily want to take it down, but you would like to get a snapshot of what's going on there and bring it to somewhere that's not production, and then poke at it and try and debug it without everything going away.
Okay, sorry. What's your definition of core in this context?
The contents of memory in the VM.
Gotcha. Okay, that's what I thought you were
The old
talking about. I just
IBM.
wanted to make sure.
And in theory, any memory that the like C extensions have allocated, like the process memory.
To me, I just want to capture a snapshot of the image and then do all of this offline.
This is what I heard him say.
Yeah, offline and potentially 6 months later if it's something that's super rare and then comes back 6 months later.
Right. I had to do this a couple times at Sun. It really sucks. But I crawled old cores, but true core dumps.
True core dumps. Yeah, I know. Just do the core dump. I mean,
but you don't have dwarf data for the objects that were made in the VM. You only have it for the C stuff.
So I went through the act of building up what the JIT knew about the code it was compiling, so I could reverse the JIT's debug info when I was looking at the code manually. That sucked. Later at Azul, I fixed that and said I could export the debug info in the profiler as an attached tool.
Right.
So now that memory's cheap, does it make sense to keep some debug information in memory that you're not actually going to use for the running of the program, but will help you make a prettier
It's only ever
core dump?
It's only ever kept in memory. If you took a core dump, you got the debug info. You didn't get the interpreter for the debug info, the interpretation of the debug info, but you got the debug info.
Right. And you can get all the thread information you want out of that.
And you can get the thread information. I'm talking about different stuff here, but there's a thread information pile. That one's a little easier to get. Here's the JITted area where all the JIT code lands. Intertwined with that is pointers off to piles of debug info. Based on the current rev of what you're JITting and what you're building and the tiny dot number of the JVM, the debug info means different things. So you need an interpreter that was based off of the build that you had at the time the core dump was made. But then in theory, you could get that and you could interpret the JITted code and you could interpret the heaps and all that kind of shit. Just heap crawlers, people have heap crawlers that exactly crawl the object debug info, object descriptor info, and crawl heaps smartly. That's been around a while.
And you can find all the stacks so that you can then go crawl the heap reasonably.
Yeah, that's pretty standard.
The failure that I got from Sun was that they tried to crawl the stacks sort of poorly, and then they tried to crawl all the debug info you could get from stacks, which is a fair amount, poorly. And so as soon as you had an adversarially close, you had a crashing VM that had something subtle wrong, all those pointers into the debug or whatever were all slightly off, and somebody crashed, nested umpteen layers deep. And then, like I said, you got crashes and the crasher and the crasher and the crasher. It was stupid.
So the tooling wasn't so robust to.
It was,
yeah.
yeah, it was horrifically worse than just giving me a fucking core dump and I'll set it up in GDB and walk it manually. So that eventually got fixed at Azul. I assume it got fixed at Oracle. And now the core dumps that Azul could get would have all those crawls done that you're talking about, all the smart crawls done, but we're robust enough to eat all kinds of, like, we just assume, which should be appointed to debug info X is actually random crap, and we'll begin to interpret it carefully as we go to validate it's actually debug info X. And if it is, we'll go to the next step and recursively, but if it's not, we'll stop and say, here's the debug info we got, but it's crap, so we stopped. And and you got partial.
And you're using GDB for that. You didn't have a tool that was like, read in this core dump and then drop me into a REPL so I could go poke at it.
When I did it originally at Sun, I did it with GDB and macros from hell for some of the parsing. And just knowledge of what the hell things worked and manually, and I skipped a lot of things. So at Sun, I put together the dump that info out onto a browser, and I kind of refined that at Azul and had a really nice way to get all that info out. But on a functioning, well-running VM that wasn't crashing. However, because it came out nicely, you could get it usually fairly robustly on a VM that was sick but not yet going down.
So the question is, like, what are the use cases that you're thinking this might be useful for? I guess I'm trying to understand.
Oh, well, so from Aaron's use case.
Yeah, not you, Cliff, sorry.
Yeah, my use case is you've got something that is crashing in production, but crashing in production rarely. And you want to make sure that you're getting that core dump and that you can take it.
Why a core dump, not a heap dump?
So you're talking like how's it?
Well, that's sort of my question is, should it be a core dump versus heap dump versus stack
dump? It wouldn't be
dump,
core dump if you're debugging the JVM.
Yeah,
heap dump if you're debugging, your Java code.
Usually in this case, we are debugging something in user space, not the JVM itself.
Right. Okay. So so typically what I see is that from some of these corrections is like you get a 6xV, right? So that's and then basically boom, everything goes, right? So that's the most common thing I see in.
I think, Aaron can correct me if I'm wrong, but I think he's talking about much higher level stuff. Like,
right,
like the JVM is fine, but user code went wrong. Where is it wrong? And then it's, an hprof and Eclipse mat.
Right.
Okay. So what kind of wrong are you looking for?
There's a diversity of wrong. Usually it starts with some kind of assertion failed, at which point you tore down the whole VM and rebooted the system and threw it back into the scheduler.
Yeah, I guess I'm just trying to figure out what type of wrong you're trying to go after here, because depending on the type of wrong, there'd be different techniques you might apply, and you might have different data requirements.
Yeah, if it's seg faulting, then I need to find what C extension is misbehaving.
Right. Yeah. And
I've yet to actually hit a seg fault that was the JVM's fault.
Or misjitted code or something like that is the typical case, right? The JITs produce code that is a bit wonky, right? But you're talking about.
Maybe I'm not writing weird enough Java. I've never seen misjitted code, at least for personally.
Oh yeah, you see that all. You can get that happening in all kinds of places. It's not really an issue. It's not common, but it does happen. I haven't done a survey here yet to see what the actual core dumps look like coming from here, but since we have like millions of JVMs running, I guarantee you I could probably have a nice database a nice sizable database that I can run through to see.
Yeah, well, the other thing is when you have millions of JVMs running, you also have memory errors and
right. Shit happens, right? So, but anyways, the question is I'm just trying to get a better understanding of what your particular use case is, because if it's just a general debugging technique, then that's one thing. I'll let you go on with your description, but if you're looking for specific use cases, then that's interesting to me. I say it's interesting to me too, because if I look at our diagnostic engine that we've been building, and we look at the diagnostic paths that come off of that engine, then certainly the type of heap dump analysis that you're talking about is interesting, but it probably makes up about, I don't know, a small subset of the total number of diagnostic paths that we'd wander down. So I'm just wondering, you know, from your perspective, what are you seeing that would make it interesting? Because
You're seeing that because most people are debugging stack traces and not bothering to do heap dump.
yeah, most people are debugging stack traces to try to solve a memory problem. That would be wrong, right? And it depends on what type of memory problem you're trying to solve.
So sometimes it's as simple as this thing is leaking memory and is having to be rebooted every 3 days because it fills the whole box.
Oh, okay, well, that's a well-solved problem, right?
But yeah, those are, we've got pretty good tools for.
Yeah.
The trickier one seems to be the thing is working like crazy, but not making any progress. And you're trying to figure out why you're not actually moving forward.
And that's a memory issue?
You can't.
I don't know.
I have seen
No,
it.
no. Well, I mean,
It's isn't it more you just want to be able to look at the state of memory,
Yeah.
right? So Aaron, I'm curious, like I assume you've gone the hprof route, or is that not
Right.
something you've played with?
I've seen hprof on something that's running, not necessarily for something that I want to snapshot and take a look at later.
Yeah, I guess hprof can mean a number of things, but the way I always look at it, it's like a traditional core dump, but just for Java, right? So you get, it's the equivalent of you stop at your debugger, you stop in the JVM in your debugger, and you can never step forward, but you can walk through all memory, look at the state of all objects, and then with the Eclipse mat tool, you can basically run SQL queries on your heap. So it's like the answer is definitely in there. You just don't ever get to step forward. And the only, I don't know, the only downside I see to them is you need a machine with as much memory as the size of your Java heap to do anything useful. And when you're running terabyte heaps, it kind of becomes not workable.
yeah, that's, I mean, to me, that's a bigger problem is that the tooling, it just really sucks when you have a reasonable size heap. And no one has actually taken a look at, you know, how can we manage to scale this? And it's certainly one of the problems we're looking at is you know, how do you scale up when you have.
In the meantime, it was a great excuse to get an 8 terabyte notebook. So
Yes.
Let's say just need more memory on your box.
No,
that's the RAM, not the
the
flash.
answer. No, Cameron. The answer is to distribute it. So that's how come I had a truckload of laptops being delivered right now.
Oh, I guess.
World's most expensive hash map.
Yes. Wow.
Exactly. I was just trying to find something here to possibly share. Maybe it could help with the thinking. But yeah, hold on, let's see if I can get it. Anyways, just continue. I will interrupt when I'm ready.
So
I'm.
I don't know. I'll go first, I guess.
Yeah, go Alan.
So one of the things I mean, so the core dumps, they actually don't have enough information on a lot of the cases, because in a lot of cases, the error in the program is a logic error. And so what you want to know is not like, what was the program doing? What structures in the data are corrupted? The question is, you know, what was the value of this variable, you know, 100,000 instructions back.
Yeah, you don't need history before you crash.
Yeah.
You throw an assert, something was wrong now. It got wrong a long time ago.
Yeah.
What the hell was it? When did it go wrong?
You just need to collect the heap dump on every instruction.
Yeah.
Fine.
Yeah. So there's this thing called omniscient debugging, which is, as the name implies, is it collects all that data. That's, I don't know, like it works for small programs.
Yeah.
You know, like, but I'm not sure what you do for large programs when it's been running for a while.
Yeah. I have this pattern I go through in life or doing a project or whatever, where I start with things are working along and I notice I got a crash somewhere and I go find a bug and I diagnose and whatever, pain in the neck, I fix. The second or third time I find a bug in around there, I throw asserts in and I catch it a little sooner. But then I get this pattern where this assert keeps finding things as I go to the next step where I run the assert in bulk periodically. It becomes too expensive, so I insert a dial knob that I can add the bulk, do everything, order in, assert on a semi-regular basis, and I can adjust the cost of the assertion check up until like I know that it's somewhere near here, and I'll just have it tick every small step, and I'll rerun this giant global assert. So there's like this series of progressions I go through of ever more expensive testing when I see a particular kind of fail come out more and more and more often. If it only happens once, I only do the one, I debugged it the hard way and got it done, walked away.
So we actually built in an assert random that is a sampling assert.
Oh, sampling
just
assert, yeah.
A sampling assert just for this use case.
Yeah.
because I've been down that same path. It's like, okay, I'd like to run this, 40-second process every time I go through this loop, which is a billion times a second. But instead, let's do it, once every couple seconds or whatever, right? So it's like, how do you do that?
Where did you get your cheap source of entropy?
Oh, pseudo random numbers. You must be repeatable. Sorry, like hardcore be repeatable, or you're in for a world of hurt. I mean, I do concurrent testing all the time. It's fucking not repeatable as all hell, and you have to deal with pain in the neck. To the extent that I can be repeatable, I make an effort to be repeatable.
Can I share my screen, Cliff?
Yeah. Oh, hang on.
Okay.
Yes, but I have to press buttons here.
Okay.
I'll try it now.
Okay, how do we do this? Stop
You have to hit share screen at your somewhere. Oh, yeah. I'm the host. I don't get your view right now.
Yeah, I get it. Okay, I'm just trying to figure. Oh, is that? Oh, there it is down there. Okay, let me show this one up here. Okay. Can you see that?
Yeah.
Excellent. Okay. So this is sort of like the type of workflows that we like to go through here. And so this is like just basically a summary view of what's going on. And you can see that really I don't know if you can see the mouse or what you can see on this thing here, but really what you're talking about is things that are happening down in this area here. And that's pretty much, I find that, heap dumps can maybe be used for other things, but it's like a less efficient view to go through for trying to fully characterize a problem. And so, that's what I was saying. I was just trying to say is like, maybe you had some insight into, how you can do it for sorting out other issues and stuff like that. That's why I'd be interested in understanding what your use cases are. Does this make sense?
Heap dumps fix or let you diagnose things in churn and live set size.
Right. Well, not churn. You can't really get churn from heap dump. But churn is something that has a different diagnostic path that we'd actually run down, right?
Right.
But whichever path we run down depends on what the dominance is being expressed by the system itself, right? So if we look at if we look at an application dominant case, then we're going to look for certain signatures in the hardware. So that's where the classifier comes into play. And what that does is it basically says, okay, we're in this domain, then we will look for something else, and then that will basically send us down through a particular diagnostic recipe to try to sort out what's going on.
Yeah, makes a lot of sense.
Yeah, so for the case you're talking about where you don't know where it is, we had several cases where problems don't show up for 7 days. Well, obviously you can't profile for 7 days, but we use a classifier out here to understand when the system had worked itself into that condition, and then that's when you turn things on.
So you have a reflective way to go ask the question, do I think the system's getting wedged?
Yeah, that's it. And it's sort of like a more formal way than the way that you mentioned, Cliff.
Oh yeah, no, I was hacking the algorithmic complexity issue, although I do it for shit that turns into other things as well.
Yeah.
But bottlenecks in like system services or device handlers go an entirely different route that I haven't formalized, that's for sure.
Yeah. Well, I mean, you can do some strange things with heap dumps. I will say that, like, we looked at how can a reader thread and hash map get basically stuck in the hash map?
Yeah, I can do that.
Yeah, but actually we discovered this was happening in one application. All we had was a heap dump from it. So somebody just sent us a heap dump. So
Was it a broken hash map?
no, the hash map wasn't broken at all, but effectively if you have a reader thread in a link in a collision bucket list while a resize is happening, then the algorithm up to JDK8 was head went to tail, tail went to head, and all of a sudden you cached one of the pointers and all of a sudden your thread's just in an infinite loop, right?
Oh, that's what I meant. You had a broken hash map. Yeah.
Well,
oh, just the one thread did that.
Well, the one thread did it, but it would do it because it would hoist one of the pointers into a register, right? You just leave it there, and then all of a sudden head went to tail, and tail went to head, and you
And then
just
it was spinning there. Yes.
it would never reach the bottom of the list, so it'd spin, right?
Yeah. I've diagnosed similar behaviors where the resize of a writer and a reader would collide, and they would pollute the linked list itself, and so every thread who was repeating the timed out transaction went to the same bucket, hit the same bucket list, hit the same cycle, and spun forever. And you one by one lose your worker threads into the same infinite list. But you're talking about a single thread got hooked, which is interestingly different version of the same effect. Yes.
Right. In this case, all we had was a heap dump. So and it was like happening during serialization. So we're able to pull the serialized data structure out of the heap and then write some custom deserialization code to basically sort it out. And that's when you could see it. Anyways.
You get a stack dump?
No stack dump.
Just no stack dump. Wow.
We didn't have anything. All we had was well, we could have got the stack dump, but it was just easier to find the data and cut it out and do some reverse engineering on it.
Yeah. Well, anyway, I was thinking what I would have done, knowing what I'm doing, it was from a stack dump, go to the JITted code and stare at the register contents and realize that he was spinning in a loop because he had a read the same value back and forth.
We had exceptionally limited access, or I had exceptionally limited access. So you did what you could with what you had.
Yeah, right. I have totally debugged giant core only dumps with no stack threads. It sucked. It was really painful.
Okay. But anyways, this is a strategy that we've used very successfully over the years, and it's very effective. It helps you find things very quickly and things that you don't expect to find.
Yeah, sounds reasonable to me.
Okay, I'll back to you.
Yeah. Yeah, interesting. All right, what else?
Kind of on that same thread, the with the reproducibility problem, when we'd have a issue that we couldn't reproduce, but it kept happening, of course, only in production.
Yeah.
Once we'd identify the data structure, we'd randomize tests against it.
Yeah.
So basically the machine would just sit there building random tests and running them.
Yeah.
And then the cool part that we figured out is that when the test fails, it needs to print out the source code so in other words, it would actually generate.
Oh, you're doing a fuzzer. You see random test generation, you're talking a fuzzer.
Right. Yeah, basically fuzzing against the suspected part of the API of the data structure or whatever. Right. So then it would create the source code to reproduce the test that just failed and spit that out so that you could then see if it was reproducible.
Right.
So
interesting. So you're not taking you always capture the starting seed and you have the iteration number in the seed. And you should be able to, in theory, press a button and get right back to the source code. But you said just print the source code out.
Right. If we were using a pseudo random specifically to generate the test, and then we just need the seed and the yep.
Yeah. I totally do the pseudo random thing because that's the quick hit to get right back to it.
Yep. No, we did the same thing recently. We introduced an explicit pseudo random so that you'd have reproducible tests just for that reason.
Yeah. And at H2O, we had to have distributed scale out, highly efficient pseudo random. So there was that thing there where you start with one seed and every node in the cluster took that and mutated it their own way. Then they fractioned it again for random numbers for every chunk of data set and every row in the column and whatever. You could get within a few small steps the random seed for a particular row that was deterministic even across a wide cluster. But that was, needed to get a big data solution going. like pseudo random, except every node had the same starting seed. Well, that didn't work because they all had the same seed. So then it was pseudo random, but they all picked from a random number generator to begin with that was current time millis. Well, that didn't work because everyone started from the wrong, different seed. No, you had to start from one seed, spray it around the cluster, and everyone go from there.
Yeah, it's pretty crazy how the pseudo-random algorithms can provide an almost inexhaustible
Now they're pretty
supply
good.
of, yeah, it's
Yeah.
amazing.
They've gotten a lot better since I was a youngster. They weren't nearly as good. Now they're a lot better. They're cheap and good and can be distributed and can jump forward and backwards in time and all that kind of shit. It's pretty good. That's fine.
Oh,
All
so
right, it's 11:40. What else?
One thing I didn't mention before was the RR debugger, which
Exactly,
is
Matt.
like,
Sorry. I'm responding to Matt's chat, which is exactly, yes.
so I put it in the list of links. But so the RR debugger, it only works on Linux because Linux is the only one that has a system call API that can be trapped. But
Reversible
basically,
debugger. Yeah, I've seen this. Okay.
yeah, so like it traps all the system calls and a lot of the concurrency stuff and makes it single threaded. And then you can just replay the program from a specific point. So it's kind of like the omniscient debugging I was talking about. It's just that he's made it practical for using for large programs like Firefox. So if you could use it for a web browser, you can use it for pretty much anything.
Mm-hmm. Okay, so it's gotten more love over the years.
Yeah, but it only works on Linux, which is, I guess, I don't know. Like, I'm not sure. Like, is Windows compatibility a thing that programming languages? But yeah, I don't know.
I have to go see. I'm looking at now TORs. Like I heard about these debuggers. That didn't have one at hotspot time, but now I'm looking at TOR's visualization of randomness.
Yeah, it's kind of cool.
Right. Oh.
You can write your library and it will generate random points and project it into a screen. So a randomness should look like noise. If it doesn't random, it will have a spot. It uses some Gilbert's curve to project one point into two point space or something like that. There is this is a technique to test the randomness of the generator of the algorithm or whatever.
Yeah. I'm looking at the interesting GIFs that come out. There's clear patterns in some of them and not in others.
Yeah,
it's totally cool visualization of randomness.
Some guy had asked me, and I haven't any idea how it's done, but I found it, so I made a library that.
Oh, what did I discover? Stupid thing the other day. So we're talking about random generators. Went and drug up. Let me correct myself. This is a better hash function. And actually worked really well. And like I stared at it for a long time. It's like, what the hell is he doing? And then read his web page, and he got pretty smart and did a lot of cool things. Where did I hide that damn hash?
Zorshift star.
Here we go. Hang on. I'll throw it into chat in the link here. Lost my chat window, lost my link window. What the fuck? Zoom meeting. Here's chat. Fine. So that's the comment in my code. Bertle.net Bob. See lookup 3. What the hell? So self-explanatory, but I use it as a hash for types in my immutable persistent data storage types, which have many types that are very, very similar to each other and only slightly different. And it does an amazingly good job for hashing this kind of shit. for very low cost. And it's the actual code that I ended up with. It's got a lot of rotates in it here. Let me go. Here's some Java code, which turns out to run pretty damn efficiently. Oh, come on. Why are you not pasting? We'll put in Google Docs. Let me try Google Docs here. So chat, where's the code window? Somebody always puts up. I'm going to slap something down in here. Oh, here it is. Sampling assert, code for copy. Okay, all right, I'll copy and do this again here. And now I lost my cut and paste. Okay, there you go. This is what I ended up having in a core utility function for producing randoms, where I collect parts by calling add hash, and then I get with the get hash when I'm done accumulating parts. And it was giving me a much better spread. And at some point, I'll probably look for a cheaper version of the same thing, but this is basically a cut and paste from Bertle Bob lookup here. And I know the JVM will take that rot and turn it into a fucking rot. So, the cost here is actually pretty minimal. We're talking whatever, dozen clock cycles for things that in my case have long, very similar prefixes. So it's hard to get randomness by just peeking a little bit here and there. You want to be, the old string hash problem. String hash worked great until URLs came along, and you have 500 character URLs that are all identical, and then the tail was different. So, the old string hash was look at the head, and then it was look at the head, look at the tail, and now you had to go fucking run the whole string through to get a decent string out. And there's better, faster ways to do it now, but it took a lesson that you need to get all the bits. And so for me, I have the same exact problem. I have a complicated large type, and I make a little diddle twit to it. I get a new type that's a little bit different from the old type. I want to diddle the hash function and get a significantly different hash so that it hashes better.
So certainly you can use a library like this to test the randomness, so it can visualize it. If you can,
I would love
it.
to, throw Bertle Bob through your random visualizer.
It does work. It does work, but you have to play with it too.
No, I want to see what it does, to see that it's getting me a good spread on my numbers. He's got a discussion that he goes through that he talks about why any individual bit being flipped smears about immediately, so that you get a good spray of bits right away. I mean, so like I had hashes in there that were doing obvious little shift left and shift right and XOR mappings, and I did not get nearly as good answers this guy gets.
I have built some pretty good just by random guessing and projecting and plotting. Are they random enough for the use cases you have?
How does it compare to like a CRC?
Oh, I have no idea. I wanted something cheap and fast. I hit on this. I tried it. It worked great for me. I walked away.
Well, I was wondering if there was any comparison with the both performance and ability to make different answers.
I have a lot of data structures that are complicated. I don't want to like serialize them for an official CRC like pass and then deserialize or whatever.
Right.
That would be more overhead than it's worth. I just reprobe in my hash table a few more times. I did end up putting in like profiling on my hash tables to confirm that I get good spread. Discovered I got bad. I got this guy. Now I get good spread, and all that kind of things come out there. People talking about performance debugging. This is definitely on the algorithm only side, but bad hash functions lead to bad hash tables, lead to bad performance. All right, here we are. It's 11:45. Anyone throw any last topic out, or I'm going to declare victory? Gilbert, you get what you wanted out of this?
I did have one other small topic, but I think it's probably a bigger discussion than the amount of time we're going to spend on it today. So I'll save it for next time.
Okay, yeah, bring it up next time.
But
Oh, good.
okay.
All right.
Well, I mean, I have a topic. I don't know how long it will take. But what exception handling? Do you want it or do you not?
You want something. I do. Yeah, different people are going to have different opinions, though. But I have a
I
very
like the.
strong.
I don't know if this is a long one or not. Let's do VI versus Emacs first.
Emacs,
So-
or I'll kick you out. See, it's a short discussion.
We will have to bring the error versus exception. What is an exception? What's an error?
Yeah, Java. I don't like what Java did. I definitely want to have a mode that says something like, I should be able to recover from this. My experience, at least in Java, big Java apps, is most people who catch an exception can actually recover. So they shouldn't bother catching because they're not fucking going to do anything about it that's useful. All right, Matt, we know where you live. I mean, we know where you came from. Go back into the swamp.
He's trolling, right? Exceptions?
No,
He's trolling.
Matt's not.
No,
Matt's
he's
trolling
trolling.
Ed. Alan's asking something legit. As far as I'm concerned, it's legit.
No,
Java
it's
did some
trolling.
of the exceptions because C sucked at it. Okay, C++ did some of the exceptions because Java sucked at it. I don't like either one of their solutions. Do I have a better answer? I don't know. I have an answer I like better until I try it, and then I'll probably hate it more. But exception versus error, I think, was stupid. Must-checked exceptions was stupid because the first thing that happens is too annoying. So you recast everyone as an unchecked exception. So you quit writing fucking and throws IO exception or whatever the hell. No, you do that shit.
Well,
Oh, no,
there's
that's-
two important truths to understand
No.
about exceptions. First of all, if they happen all the time, they're not exceptions.
Exactly. Yes.
By definition. So that's
Yes.
number one.
Yep.
And number two, looking at the Java hierarchy, can you give me an example of any exception that's not a runtime exception?
Oh, I'd have to go look.
Because running out of memory is an error, but it happens at runtime. So I would call that a runtime exception.
Oh, I
And
see.
everything there is no such thing as anything that's not a runtime exception
Okay.
by definition. So exceptions should be exceptional. And of course, they all happen at runtime.
So
Yeah.
runtime exception is just badly named and we grant you.
Well, there's only three hard things in computer science, which is off by one errors and naming.
Yeah.
Yeah. Invalidating of caches. That's the other one.
Four
I
hard
will-
things.
I will throw my money on a totality of functions instead of exceptions. So
What do you mean?
I mean, if it returns a number that it has to be in some kind of range, it's an option of a number if it's outside the range. That ensures the function is total. It cannot return anything that it's not supposed to return.
Is that kind of like a dependent type system?
No,
No,
she's saying
no,
the
just an
functions
option.
don't throw exceptions, they return a value.
Yeah.
But the value includes an indicator that an exception happened.
Mm, So for that you have either has an exceptional type and an
Yeah.
return type. Yeah.
Or result, I've seen it called result, option.
Result
bunch of
left
things, yeah.
left. Yeah.
So you're talking about, if you only get to return one thing?
Yeah.
What
So-
language would have that limitation?
Not to
Yeah,
mention
yeah.
Java or C, or most of them. have-
I pick yellow.
Yeah,
I pick yellow.
okay. I'm of the opinion that I want to enforce that exceptions are for exceptional situations. So file not found is not exceptional. I can deal with it as a
Right.
normal error code. Running out of stack space is exceptional, but probably not recoverable. Running out of heap is exceptional, mostly not recoverable. Throwing an array index out of bounds exception probably wants to go to your debugger, probably is not recoverable in general. On the other hand, there are occasional cases where people would rather do that than fucking test for it. But you don't want to test for it every time you do an array reference. Way too many times where you check and be totally legit. You don't want to deal. So you need some low syntax way to say an array index out of bounds can be thrown. I'll take this entire piece of my subprocess and toss it. This is Cameron's model for ecstasy, and go again because I'm doing a web server and I can recover from random web requests. I can't just recover from arbitrary Stack
Right.
Overflows or whatever.
My favorite one, end of file.
Oh, why?
Like
yes.
which file doesn't have an end?
Yes.
And it certainly is recoverable.
All right, so there's a bunch of bad things that turn into exceptions in Java land, no question.
No kidding.
But how do you come up with a way to say, I believe at this point I can recover from some arbitrary error that happened before. I want to declare that, I want to catch the exception, I want to recover and carry on without allowing people to go down the path of, I'm going to throw and catch every possible thing because I don't care performance or whatever. You know, like hard and fast guaranteed. If you throw an exception, I put a 10-second delay in before I recover.
Cliff, I think the thing is, I think you're taking a huge assumption of context and stuff like that. Recoverability depends upon concept.
Yes.
And that's that was supposed to be one of the separations between like error and throwable, I guess.
Right.
You know, was that the errors were to cover context where, you know, the end user couldn't possibly recover from the situation. That was an intractable situation that occurred, right?
Right.
Everything else is, well, I don't know the context, so I'm just going to tell you what went wrong, and then you're going to decide how you want to deal with it.
Yes.
Right. And that was the distinction between having like checked and unchecked errors.
Right.
And that distinction has never really been understood by people who are creating these things.
Well, I don't think it panned
So now
out.
you get into this like wonky place where I have to deal with things that are coming at me by surprise, unexpectedly, as opposed to things that are coming at me by surprise because, you know, like something beyond my control went wrong. And so having everyone now decide that they're going to wrap unchecked exception, or sorry, checked exceptions and an is to me, it's just like a, you know, we just don't know what the fuck we're doing, so we're just gonna like mess everybody up by mixing both modes.
You know, I'm trying to say, can't there be a better way?
Yes.
Some exceptions are reasonable to recover. There's some places in your program can be reasonably recovered from. Most cannot.
That's not true. That's absolutely not true. I do a lot of useful work where exceptions happen because I take data from people. I have no control over the input of the data, what the data looks like and stuff like that. And, you know, you try stuff. And sometimes you're just, well, okay, this is a bad exception. In the
big data company,
libraries, but you still get exceptions thrown at you and you look at it and go like, I don't give a fuck. I'm going. I don't care. I'm going.
H2O would eat big data sets all the time that were malformed, and we dealt with that as an error code, not as some sort of Java exceptional thing.
Well, it doesn't matter. You still had to go check it to see, did this work or not?
So
you have the signal.
There's two different aspects, though.
The system is telling you it didn't work, or I got to manually go check and say the system doesn't.
That's where I'm trying to get to.
Which one is better? It's both code.
Where yes, sometimes. Sometimes the check wants to be propagated through without me fucking looking at it and coding it every time.
Right.
Sometimes I want to stop and say, and no, here we have to make a decision about what we're doing.
Excellent. So that's why I've picked yellow.
And what I'm trying to come around to is the Java model makes it hard to return an error code. So people throw an exception and then they have to check it constantly and say, and I also throw, and that's too much overhead. But there should still be a place where I want to stop the exception getting thrown.
Yeah, but then again, that's like bad education, right? It's like, you know, why am I going to catch and rethrow?
Okay,
just
fine.
Just let it throw.
So I'm busy writing a new language. What should I do that doesn't encourage bad education practices? I'm trying to do something different here.
Okay. You should try somehow to, if you chain the functions that each have to check the exception, you have to propagate it to the start. So you check it only once to the function call stack. That would be a good thing.
Like lambdas, right?
Yeah, something like that. Yeah.
So I'm currently in the zone where if you're going to throw an exception, like an array index out of bounds, I'm going to demand that at a compilation unit boundary, so called a module boundary, arbitrarily where the fuck a module is, you must catch no modules can throw an exception. You must catch all exceptions and return a code. And if you call a function from another module, you will only get a code back, never an exception.
I still pick yellow.
Okay, fine. That's not helpful. I'm looking for somebody to tell me this is a stupid plan. It's a smart plan, or it's an irrelevant plan. I heard from Cameron. It's an ignorable, irrelevant plan.
Oh, okay. I'll tell you mine.
It's not yellow.
I want to hear. Yeah, Alan, go.
so my plan. So okay, so Haskell, which is of course my favorite language, has this history of treating exceptions as values. Okay, they don't actually treat them as values. They implement them as the usual, stack unwinding thing. But semantically, they came up with the semantics of exceptions as values. And what it is that an exception behaves exactly like a return code, except if you try to evaluate it in a context where you weren't expecting an exception and handling exceptions specially, then it propagates up the stack and goes
unwinds and returns again. Yeah. So it's as if a value, except there is a syntax efficient way to say, if this was the exception value, immediately throw, and you do nothing and you just do something and immediately throws it. That's fine.
Right.
That makes sense. Yeah.
So it's like, so it's like, it's a value, except that it propagates up the stack if you weren't expecting an exception. So, I don't know.
Okay.
I mean, the only problem with this is that Haskell has lazy evaluation, and it turns out the order of evaluation is not defined. And so so if you do something like throw exception A plus throw exception B, then semantically, it's not defined which exception you get.
Yeah, right, fine. You can fix that. That one could be fixed, maybe.
Well, I mean,
yeah, it sounds like they were just being lazy.
Evaluates the left one first, but the problem in Haskell is that you can evaluate sub-arguments regardless, because it doesn't actually fix the order because laziness means that you can evaluate any reducible expression rather than just the innermost expression.
Right.
So
what I was going to say earlier is that there's kind of two different issues around exceptions, and one is issues is the wrong word, but exceptions are used often because it's too difficult to communicate an error by a normal channel. And that's inexcusable. I mean, we can fix that with language design and whatever. But the other one is actually much harder. And it has to do with composability of actions at a distance, right? So what ends up happening, so let's say I have some library I'm using and there's some other library that it uses and some other library that it uses, and it calls my code. And I'm up here in my code. So my code is sandwiched around layers I don't own. And quite often people use exceptions for a non-linearity of panic, if you will, kind of a get me the hell out of here 10 levels up, right? And it's that discontinuity by composition that makes exceptions tempting to use when they're not actually exceptional. So it's about control flow, and it's a very poor, exceptions I would argue are a very poor non-exceptional control flow mechanism.
Yeah, I've seen them used that way too.
By that you just mean exceptions as long jump.
Yeah, I would call them an overreach. Most of them are like an overreach. So what do you mean by composability of actions at a distance? I had to write that one down because
it sounds cool.
Yeah,
it sounds so cool. I have no clue what it is.
Well, composability meaning that I'm taking functionality that's been built by different, so I'm going through a pipeline where the pipe is actually being built by other people, right? So it's like I'm composing, and at the end of it, it's being composed with something that I've fed in maybe from the start of it, right? So it's the ability to glue things together, but then something surprising happens down there that nothing in between was intended to deal with. So it's at a distance, right? Because I started up here, in between is a bunch of other people's work, and then at the end is my work again. And it's like there's
you can imagine
Unix shell scripts. Excellent.
You returned a value from your thing that was the Haskell, I'm an exception, except if you peek at me, I'll throw. But if you don't peek at me, I'll just pass it along. Then the in-between stages have a black box. They're not looking at anyhow, but they're moving it around, shoving it left and right, storing it, hang on, not, whatever, fine. They eventually unwind back to you. And you go and fetch the value your thing earlier had called. At the time you fetch it, then you throw. But the layers in between don't know an exception happened, don't care, don't want to. They want to do what they want to do. if you forcibly unwind an exception through them, they don't get to recover any state. But they could execute properly with whatever return black box you got out of them, as long as they didn't peek into it.
Yeah,
If they
just
peeked into it, they're going to start throwing too.
to talk about the composability a little bit more, because we've got enough Java people on the call, this will make sense. Before Java, there was, and Kirk, you can leave small talk out of the conversation. Before Java, there was no composable software.
Goodbye. We're out of here.
I knew he'd take offense, but the point is, like, say in C, for example, we had boundaries.
Mark.
Like if we built a DLL, for example, it had its own malloc internally. And if I called another DLL, it might be using a different malloc because it might be statically linking the C runtime line. And there was no rules there, so we were all in our own little fiefdoms, every library, every person's code.
Rules are worse. Library, DLL1 calls DLL2 and gets a pointer, and DLL2 says, I'm done with it, I'll free it into my own heap, and it came from the other guy's heap.
Or it's even worse because DLL1 was written with a medium memory model, and DLL2 was large. Like
usually those crashed like right away.
Well, I was good at crashing those. But the point is with Java, even though things were compiled separately, they were, and I'm going to munge some words here, but they were all run in the same global space. By the same global rules. And in fact, all of Java's issues around exception handling, I really think, are bound to the unseparability of these domains. Because when we talk about exception recovery, it's not recoverable or not. It's recoverable at a fault line, and that fault line has to do with separability. So if you don't have designed in separability, it's hard to predict recovery.
Finally, something I agree with. Excellent.
I think as hard as Cameron is about how to make my fault lines clean and precise and recoverable. Maybe I should. I don't know. All right, I'm going to claim victory, and this is a great conversation.
Simon has to the last word.
Well, Kirk needs the last word because he has to tell us what we're going to talk about next time.
How to reorganize your binaries and its effect on performance.
Oh, I as usual, I have direct experience with this, but and really old stuff, but still relevant. Fine.
Okay.
Sounds good. Sounds like a great topic to open up next week. I'm going to declare victory for the Alliance and hope to see everyone next week. All right. Bye-bye.
Bye, everybody.
Bye.